Gravity is a fascinating force. It's what holds everything on our planet together, and it might one day help us travel to other planets. Gravity is a strange thing. On the one hand, it's the oldest and best known of the fundamental forces. On the other, it's the weakest and least understood. Within that uncertainty may lie the keys to escaping this world and traveling to countless others, or building structures of incomprehensible scope and amazing purpose. While we'll cover gravitic technologies beside propulsion in February, today we'll focus solely on moving spaceships. We'll explore everything from mundane uses of gravity for propulsion, like slingshotting around planets and the Oberth Effect, to more hypothetical varieties, such as space-time warping, gravitational wave propulsion, anti-gravity, dark energy, negative matter, frame dragging, the diametric, differential, pitch, and bias drives, and more. That's a lot to cover, so grab a drink and a snack, hit those like and subscribe buttons, and let's dive into the topic. We might as well begin with the best known use of gravity for moving spaceships, preventing them from moving by giving them a massive gravity well to drag themselves out of, while also making them drag through a thick atmosphere. This is where something like anti-gravity could change the game. If you could simply ignore gravity or activate something that counters it, it would be revolutionary. Anti-gravity is a somewhat vague term, mainly from science fiction, and probably should be divided into reversing gravity and nullifying it. This brings up a key point about gravity. Unlike other forces, it lacks a repulsive aspect, only having an attractive one, or so we think. We could be wrong about that. The mysterious force known as dark energy, for instance, acts a lot like a repulsive gravity force, and we'll explore that later. The ability to manipulate gravity would be a huge game changer if we had it, but it's worth noting that we already have some ability to manipulate gravity and even some forms of gravitic propulsion. Let's delve into three existing techniques: gravity assist, also known as the slingshot maneuver, the Oberth Effect, and tether propulsion. Most people are familiar with gravity assist or slingshot maneuvers, but the mechanism of speed gain and how it varies with the Oberth Effect can be confusing. The gravity assist slingshot and the Oberth Effect are both important techniques in orbital mechanics that allow spacecraft to gain speed or change trajectory efficiently. However, they operate under different principles and in different contexts. Here's a breakdown of their differences. A gravity assist or slingshot maneuver uses the gravitational field of a large celestial body, like a planet or moon, to change a spacecraft's speed and direction. As the spacecraft approaches the planet, it falls into the planet's gravitational well, gaining velocity. This is part of why asteroid impacts are so severe. Even if an object is moving at the same speed as Earth when we cross paths, it will generally gain velocity relative to us, comparable to Earth's escape velocity, as it falls into our gravity well. When the spacecraft exits on the other side, it has gained energy relative to its initial trajectory. Essentially, the spacecraft borrows some of the planet's orbital momentum, giving it a speed boost without using its own fuel. People often understand why this lets you change direction without fuel, but they might wonder how it can increase speed. After all, if you fall past a planet, you're moving away from it again, so shouldn't you lose the speed you gained? And the answer is yes, but only relative to that planet. That planet is moving around the sun, or the sun around the galaxy. Imagine hooking a physical tether to a planet like Jupiter as you cross paths. You'd end up in orbit around it, and in fact, we'll discuss using a physical tether shortly, but for now, you're latched on. Picture this tether as being made of virtual gravitons. When you go, let's say 10 kilometers per second, away from the sun, toward what we will call solar east, assuming the sun is at the center of the map and compass directions align with the sun's ecliptic. If you hold on to that for half a Jupiter year, you could release on the other side of the solar system in any direction. Jupiter, like most celestial bodies, orbits on an elliptical path, moving faster when near the sun and slower when further away. This allows you to change your velocity relative to the solar system, or even the galaxy for interstellar slingshots. You're riding along with someone else as that body changes speed. The maximum gain is twice the celestial body's speed relative to the Sun. The momentum gain depends on the object's mass, how close you approach, its speed relative to the Sun, and the incoming and outgoing trajectories. Voyager 1 picked up about 10 km per second from Jupiter, which orbits at 13 km per second. Cassini, during its mission to Saturn, managed to fall toward the Sun, use Venus, revisit Venus again a year later, then slingshot around Earth, and finally shoot out to Jupiter, which it used before reaching Saturn in 2020, 7 years after launch. Mercury is an optimal object for slingshot maneuvers because it's small, dense, and orbits faster than the other planets. With good timing, you could fall from Earth, swing past Mercury, and fling yourself out of the solar system, possibly passing by other planets along the way, though this would be slow on an interstellar scale. It helps save fuel on launch or on arrival to slow down. You could further speed up after slingshotting using conventional fuel, or vice versa on arrival. By slingshotting around stars or black holes, you could achieve impressive speeds, potentially approaching a fraction of light speed. But this requires us to move from a passive slingshot to an active one using the Oberth Effect. Now, the Oberth Effect does involve using fuel and lets us get more out of it when moving toward another body at higher speeds. That can seem weird, that a spacecraft gains more kinetic energy from a propulsion maneuver like a rocket burn when it's moving at higher speeds, particularly when it's deep within a gravitational well such as near a planet. If we picture a ship approaching a planet or in a long elliptical orbit, it is speeding up as it falls toward the planet and slowing down away from it. If at the top of a long elliptical orbit you burn fuel to finish breaking away from it, which is what we tend to visualize, burn to get free, you will actually do worse on this than burning as you drop toward the planet. So let's imagine we're moving toward a planet to get some gravity assist and turn direction, hooking around it. It's weird to think about, but the amount of speed you get from gravity is based on how strong the field is and how long you spend in it. Just like any force, more time under it, more strength, faster speed. If you are approaching a planet at speed, you will pass by it faster and spend less time in that gravity. This normally balances out if you're not burning fuel, because you might pass by in an hour or a day, but you approach it, gaining speed, and leave it, losing speed, in the same time interval. If you are falling toward a planet and not burning fuel to speed up, you spend a lot of time falling. Now you burn fuel on your way out, speeding up using it, and while at top speed too, so the time you spend leaving, being pulled on by gravity to slow you, is decreased. This cuts the period of time when gravity is hurting you most, pulling back on you while closest to it, and when it's strongest. And this is one way to look at the Oberth Effect. Another is that when you burn your fuel, you are going to increase your speed by a set amount of delta V. Let's say you're approaching Earth initially at 0 speed, and you've got enough fuel to give you 5 km per second of delta V. Left to yourself, you're going to be going 11.2 km per second when you pass Earth, then lose all that climbing away. That's our escape velocity, and it reflects the energy you gain then lose from gravity, or 62.72 megajoules per kilogram. Accelerate from the beginning to 5 km per second, adding 12.5 megajoules of kinetic energy per kilogram of ship. Instead of reaching Earth at 11.2 km per second, you will be going 12.25 km per second and be at 75 megajoules of kinetic energy. We must then spend 62.72 megajoules to escape Earth again, and that leaves us right back down again at 12.5 megajoules of kinetic energy, or at 5 km per second, when we are done. Simple conservation of energy there. But if instead we use that delta V, right after we hit that maximum fall speed of 11.2 km per second, we are now up to 16.2 km per second, and now our kinetic energy, which goes with the square of velocity, is up to 131.2 megajoules per kilogram. Now we pay that 62.72 megajoule energy tax to leave Earth, and we are left with 68.5 megajoules per kilogram. and that is a kinetic energy equivalent to 11.7 kilometers per second, not the 5 kilometers per second of delta V our rocket fuel offered. And that extra energy comes from the gravity of the planet you passed, or any celestial body, so if I'm falling toward a black hole and burn when I'm moving at 10% of light speed, and having a kinetic energy of 450 trillion joules, ignoring special and general relativity for the moment, and that 5 kilometers per second delta V increases your kinetic energy by 150 billion joules, thousands of times what our last example did, and for the same rocket fuel. Now you have that left over when you fly off, which you can since escaping a black hole works just fine so long as you don't cross that event horizon. You have 150 billion joules of kinetic energy per kilogram, and your velocity change isn't 5 kilometers per second when you escape, but rather 548 kilometers per second, 110 times as much, and about 2% of light speed. And we could have dropped even closer to that black hole, assuming its accretion disk wasn't a threat and its tidal forces not too bad, and thus emerged even faster. Pretty impressive and using no new technology, and I should note that close approaches on places like Jupiter or the Sun can do good for us, if not as much. The same trick works for deceleration too. You fall into a system at high speed, approaching your destination, drop to that system's sun, and burn backwards, lowering your speed by a set delta V and shucking off tons of kinetic energy in the process, and again, this transfers energy by gravity. A big reflective solar sail works great for this, since the force on it is highest when closest to a star. As for tether propulsion, also called momentum exchange tethers, this comes in a variety of forms, but two channel regulars will be familiar with already are the classic space elevator and its abridged cousin, the skyhook, also known as a rotovator. You may see those episodes for a deeper dive of those approaches. But one that folks tend not to think of is connecting a tether to a spaceship from a space station or asteroid and using that to winch them in or slingshot them out in a much more traditional sense of that term than the slingshot maneuver uses. If you're wondering how this uses gravity, it's working with that in combination with a tether to allow some trajectory changes you couldn't normally do with just gravity, or at least not without burning a lot of fuel. You could basically fall toward a planet or other celestial body, get harpooned with a tether, or harpoon it with a tether, and use that and the fall to swing onto a new path and with additional speed. No special new science is involved here, other than that very strong tensile materials and very good coordination help. But on to the topic of things involving new science, or reasonably new science. I was talking about using black holes a bit ago, and very dense objects like black holes and neutron stars are great for slingshots and the Oberth Effect, but they also rotate very fast. Your typical pulsar or neutron star doesn't take a day to spin like Earth does, or more like a month for our Sun, but a second, or even less, mere milliseconds. Black holes are even denser and faster, and both objects can create significant frame dragging. Frame dragging, also known as the lens-Thirring effect, is predicted by general relativity, and we have confirmed it even around Earth itself, where it is far less. In general relativity, a massive object distorts the fabric of space-time. If the object is rotating, it doesn't just distort space-time, it also drags it along in the direction of its rotation. Near a rapidly rotating mass, space-time itself is twisted in the direction of the rotation. This means that objects in close proximity to the rotating mass experience a dragging effect, where their paths are slightly shifted due to this twisting of spacetime. You could potentially surf along this to gain some speed, as an additional option for ships moving near large bodies, like slingshots and the Oberth Effect. It would just stack up with those two to get you even more free speed, stolen gravitically from the larger body, or dumped into it to slow a ship instead. But like those, this depends on timely maneuvers taking you to objects, not a novel form of spaceship drive. We've talked about creating micro black holes for propulsion before, usually by hawking radiation or feeding matter into a black hole for high energy emissions exceeding what nuclear fusion could produce. However, if a spacecraft could generate a miniature rotating mass, with sufficient density and speed, it might be able to create a localized frame dragging effect. This generated effect could potentially be used to provide thrust by twisting space-time around the spacecraft itself. This is the basic notion behind theoretical drives like the bias, diametric, disjunction, and pitch drives, which are more concepts than a specific engine. In this case, what frame dragging can be thought of as doing is making it so gravity is stronger in one direction of your ship than another, so that you're basically going to follow that direction. We'll give some specifics on that in a moment, like how negative matter might serve as a gravity drive, but before I detail that, a neat thing about gravity drives is that they are working on everything in a ship equally, barring tidal effects, and thus allow safe high G acceleration. Normally, when we accelerate an object, the various bits of it are not experiencing identical force at the same levels and instance. This causes a lot of stress on bodies and ships that a gravitational field does not, so a lot of our normal limits on acceleration rates go away with gravitic propulsion. If you're falling in a 100G gravity field near some dense body, you're fine, whereas a person on a 100G rocket sled is going to die. And a ship that suddenly slams at 10G to the side to dodge some piece of space debris is going to injure or kill its crew, as someone who was walking down a corridor might suddenly slam a meter to the side at 10G, or 14 meters per second, 31 miles per hour. That's the equivalent of falling 10 meters on Earth or 33 feet. That could also just as easily be falling up a couple meters onto your head, or the equivalent of dropping 20 meters or 66 feet and landing head first. You wouldn't have that with a ship accelerating in a gravitational field unless it was so sharp and narrow we had the kind of effects we experience near black holes, where gravity on your feet is significantly higher than on your head and rips you apart. Gravity pulls on everything equally and is stopped and slowed by nothing we know of. It's not a force we can block like we might an electromagnetic field. If we could, that would be a path to anti-gravity, or even gravity beams or waves or gravity lasers. You float off a planet because your gravity-reflecting paint on your ship pushes you away from gravity or prevents it affecting you. And this was the method used in H.G. Wells' 1901 sci-fi novel The First Men in the Moon, where the substance called cavorite negates gravity. And such a material, or field you could produce, opens the doors to the classic flying saucer ignoring gravity, or to neat gravity-ignoring suspensor fields that let you move heavy objects with ease, or fly around in the sky without wings, or even build citadels floating in the sky. Again, we'll cover that more in our Gravity Tech episode. A material like cavorite would be problematic in our universe, since it would flat out permit you to violate conservation of energy. But we've known that's had some exceptions since nearly when the book was written, as conservation of energy has some issues with things like general relativity, Hubble expansion, dark energy, and of course the Big Bang itself. So we should not take for granted that conservation of energy rigidly prevents workarounds. The laws of physics may be inviolable, but if there are loopholes we could exploit, there is no sign of an intelligent policing agency enforcing obedience. It's just that something like cavorite also allows perpetual motion machines, which is itself a way to run a spaceship drive, and thus would be a type of gravitic propulsion too. There's a lot of ways some piece of clock tech, hyper-advanced borderline magical technology, could allow us to move ships or generate power, but there are some general approaches that we should highlight. The first is the bias drive, which is an example of a clock tech engine that works not by warping space or time, but by locally altering physical constants of the universe, in this case the gravitational constant, in front of and behind the ship, letting it essentially fall to its destination. Gravity becomes inherently stronger from one direction by altering that constant to be bigger, like the ones covering the electromagnetic force are. This might involve something weird like finding a parallel universe that had a higher gravitational constant and sliding toward or into it, or skimming or skipping along it. In the case of warping space-time itself, this can provide normal propulsion and potentially even faster than light propulsion or time travel, but see our Warping Reality episode for discussion of warp drives in detail. Beyond having no method to alter physical constants at this time, it is likely that a bias drive would produce a singularity in the center of the ship. If functional, however, such a ship would not need to expend any fuel to move from point A to B, and a bias drive would appear to allow perpetual motion machines for producing electricity and power, though it is entirely possible that techniques for changing physical constants might still conserve quantities such as energy and momentum. We also have its cousin, the Diametric Drive, another hypothetical clock-tech reactionist drive, but one typically envisioned as running on negative mass, and it is actually a subcategory of pitch drives, which we'll get into in a bit. The basic notion here is that you build a ship stretching between two big globes, one of positive, regular matter, and one of negative matter. The former might be where all your people and cargo were at, and it does not have to be of the same mass, or rather opposite mass, as the negative mass section. In the most commonly discussed version, it is generally assumed that positive mass will attract both positive and negative mass, and negative mass particles would repel both positive and negative masses. As a result, two positive mass particles will pull toward each other, two negative mass particles repel each other, and a positive and negative mass particle will actually shove the positive mass away from the negative mass, while pulling the negative mass toward the positive mass, resulting in the positive mass particle being chased by the negative one. So a ship running on this, a type of diametric drive, will begin falling towards positive mass globe on the front of the ship. You could flip over to slow down, or more likely just have several of the globes, positive and negative, as packets you could pump around the ship like a fluid, and rotate or stop the ship as needed by adjusting the distribution of that negative mass. Your ship might be a ring or torus instead of a barbell. Now, negative mass propulsion is a catch-all term for any drive that relies on the properties of negative mass, generally how negative mass or energy should warp space to expand around it, opposite of normal matter contracting space around it, or be pushed toward you if you shove on it, not away. As no negative mass has ever been detected, any negative mass technology currently qualifies as clock tech, and this includes most warp drive and wormhole proposals. There are multiple versions of how negative mass should operate, depending on if it is negative inertial mass or gravitational mass, active or passive, or some combination thereof. Mass is thought to really be three different items, that presumably all linked at some core level, but which we might be able to tweak separately for movement. So inertial mass is how things respond to force shoving on them to speed or slow them. Force equals mass times acceleration, and mass here is inertial mass. If I could temporarily lower something's inertial mass, it would be easier to push. Momentum is mass times velocity, and again, this is inertial mass here, and due to conservation of momentum, if we lowered something's inertial mass temporarily, then it would speed up, and if we increased it, it would slow down, with no use of fuel either way. This would be neat since a ship with an inertial mass modulator would be able to use fuel to speed itself up, get clear of orbital space, flip on its inertial mass reducer, and suddenly leap up to speed. It could then flip it on near an object it wanted to study, and turn it higher, to instantly slow down, and presumably like with gravity drives, slow everything uniformly so the crew didn't smear on the walls of the ship. This would seem to massively violate conservation of energy too, but maybe it's robbing it from something else, and indeed it would be awesome to use in conjunction with the Oberth Effect. But that is inertial mass, active and passive gravitational mass. Active is how strong an object pulls on others with gravity, and is based on its mass, or its active gravitational mass if the three can be separated, while passive is how things respond to gravity. If I can dial up a ship's passive gravitational mass, it will accelerate faster as it falls towards some bigger object. Then, like with the timing and using the Oberth Effect, I can switch it low as we pass that object, and it begins trying to pull us backwards, but with weakened effect. Active gravitational mass alterations could let us generate a tractor beam to pull toward objects or pull them to us, and indeed you might be able to make a gravity laser at that point, to concentrate it at a great distance to yank on somebody and pull yourself toward it or it toward you, or for bases to shove ships away to launch out of a gravitic cannon, so to speak. Possibly a device more worthy of the name mass driver than the one we usually discuss in that role. See mass drivers for details. If we can manipulate these or make gravity lasers, we must consider that we may be able to generate gravity without mass at all, and this is the concept behind the Disjunction Drive, that a field might be disjoined from the object that created it, in this case gravity and mass, but it could be one of the other forces. Conceptually, we might imagine a ship built near a large gravity well, which was then disjoined from the mass creating it and potentially reattached to the front of the ship so it constantly fell forward. We might also disjoin something's inertial mass while leaving its gravitic mass in place, or disjoin an electrostatic or magnetic field from their generator. This could also be a disjunction from a Higgs boson field. Needless to say, if I can lower or raise something's mass, in one or all of those three roles, it may be possible to lower it to zero or even below zero, which takes us back to negative mass or negative energy propulsion. And again, we don't have any negative matter. I personally doubt it exists, so we can't be sure of its properties. The pitch drive is a hypothetical Clark-Tech reactionless drive where a field or force can be used to create an effective pressure difference on the ship to push it along. Diametric drives are a subcategory of pitch drives where there is a source for the force, like a ball of negative mass. Pitch drives in a wider sense do not require a source and would include technologies that simply cause some force or pressure difference to appear on your ship. It may work on any field or force which can be used to create an effective pressure difference on the ship to push it along, much as an airfoil in the atmosphere works. And gravity drives don't need to be limited to spaceships either. Conceptually, you might imagine that on one side of your propeller, gravity is 10% lower, and on the other side 10% higher, so that as they spin, the falling side feels more gravity while the other gets less. And now it can spin without needing any fuel or motor. It just spins under gravity, propelling your ship through an atmosphere. This blatantly violates conservation of energy, but again, not our concern at the moment. Of course, the dark energy that drives expansion of our universe, which itself seems to have gotten energy from nowhere to begin with, seems to violate conservation of energy. That's debatable, and we looked at those arguments in our dark energy episode, but what's undeniable is that galaxies are moving apart, and that the further you are away, the greater your speed. We assume that this is because new bits of space-time are randomly popping up everywhere all the time, and that as a result, over long distances, predictable amounts of new space are merged between objects, causing them to be further apart over time, which is speed, a growing distance over time. This is not limited to the speed of light either. If we could control or manipulate that, we could put space directly in front of us, or perhaps remove it. Space-time costs actual energy to exist, so adding new bits means energy went in there, and if you could eat some up in front of you, your distance would shrink and give you energy as you gobbled it up, presumably. Somewhat akin to the Bussard-Ram scoop, which drags in hydrogen particles along your journey through interstellar space and fuses them for energy to run our ship and its engines, only here it's gobbling up space-time. There's only about 1 joule of energy per cubic kilometer of space, which is really tiny, but there is a lot of space, and more of it emerging constantly. So a ship that wanted to generate a 100-meter radius cylinder of space behind it would only need 1 joule for 53 kilometers of new space there, and this is the kind of space-time warping that gets around light speed. So a 100-megawatt fission reactor powering some rotating habitat spaceship 100 meters in radius, and however long, could in theory be traveling at 52 billion kilometers per second, or 17,666 times the speed of light, which would mean the trip to Alpha Centauri would take just over 2 hours. It's a bit over 2 light years per hour, or a bit under 50 light years per day. You could get to the Andromeda Galaxy in a little over a century and to any corner of ours, including the Magellanic Clouds, in under a decade. That was a pretty arbitrary power supply and radius too, but we can of course build 100 megawatt reactors and a ship of that size. Now, dark energy isn't exactly gravity propulsion, but there's a strange relation there, with one only being attractive and the other only repulsive, and both being incredibly weak, but dominating the universe in their ranges. Because the other forces all have attractive and repulsive versions, they negate out much beyond the molecular scale. Even what we think of as powerful magnetic or electric fields represents only a very tiny bias where almost everything else is balanced. Beyond that, gravity dominates and is all attractive, and beyond that, dark energy does. And both are tied into space-time at a fundamental level, apparently unlike the other stronger forces. They may be unrelated, but it felt like a good place to wrap up our discussion of gravitic propulsion, with an FTR version and some hard numbers and calculations. I doubt you could just make a cylinder of space like that, more likely you'd have some more energy-intensive cone, but it's all hypothetical anyway. Sadly, that is still true for most of our gravitic spaceship propulsion options, though as we saw today, gravity is already a valuable tool for propulsion even now. What's more, gravity is still such a mystery that I am more optimistic that as our understanding of it grows, that doors to new, novel, and awesome propulsion will open up for us to fall through to strange new worlds. We never know what awesome new techs might help us in the future, like the gravity drives we looked at today, but in the meantime, there's a lot of work to be done paving our way to other worlds and helping with this world's problems. Many folks would like to help make a positive impact on the world, and using your job to do that is a great approach. After all, you have 80,000 hours in your career. That's 40 hours a week, 50 weeks a year, for 40 years. It's a lot of time to make a difference. But how do you find that job that really will make a difference and is right for you? That's where 80,000 Hours, a nonprofit, comes in. They spent over a decade conducting research, partnering with academics at Oxford University to figure out how you can have a fulfilling career while tackling some of the world's most pressing problems. They provide all of that for free, solid data-driven guidance and advice to help you help everyone else. Whether you're just starting your career, thinking about switching paths, or just want to make a bigger difference where you are now, 80,000 Hours can help. They offer tools like a free in-depth career guide to help you create a personalized plan, a job board with hundreds of high-impact roles, a podcast featuring deep conversations with experts about solving global challenges, even an episode on solving the Fermi paradox. If you join the newsletter now, you'll get a free copy of their in-depth research-led career guide sent to your inbox. Just sign up at 80,000hours.org/IsaacArthur. Stop settling for generic career advice and platitudes. Get started planning a career that works on one of the world's most pressing problems. Sign up now at 80,000hours.org/IsaacArthur. As a quick side note before we get to our upcoming scheduled episodes, this episode airs on December 15th, which is my mom, Jean's 75th birthday, and I want to thank her for, amongst many other things, giving me that early interest in both science and science fiction, without both of which there wouldn't be this show. Speaking of the show, we've got plenty more episodes still for this year, starting Thursday with an extended and updated discussion of space elevators. After that, we'll be returning to the Fermi paradox to ask what very high-tech and autonomous civilizations might be like in the Hermit Shoplifter hypothesis. Then we'll wrap up 2024 with some predictions for the future, as well as some discussion of how to make decent predictions. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show by becoming a member here on YouTube or at Patreon, or check out other ways to help at isaacarthur.net. Until next time, thanks for watching, and have a great week.